All right, for problem of the day number 2, we're going to be performing Friedel-Crafts Alkylation. And we saw this mechanism yesterday. It's pretty straightforward. And I'm going to show it using a little bit of shorthand notation. So I'm not going to draw out the p orbitals on the aluminum trichloride just because it takes too much time. So the first step is we have the aluminum trichloride interact with the chlorine. And so the lone pair on the chlorine will add into that aluminum p orbital. And when we do this, we make a new ionized aluminum species. Oh, sorry. AlCl3. So the aluminum has a negative charge, the chlorine has a positive charge. And then the next step will be this chlorine popping off. And I'm going to even shorthand this more and draw my benzene ring with the circle in it just to save some time. All right, the trick is, what's the next step here?
We're doing it again.
Hydride shift.
Hydride shift. If we look at our carbocation here, it's a primary carbocation. Primary carbocations are quite unstable. So what I'll do is, So what I'll do is I'll draw the hydride in blue, and we'll show it shifting over to that carbocation position. And why didn't I do a methyl shift?
Because what? Why would you do that?
Yeah, why wouldn't you?
Does it make more?
So I saw a few people trying to do methyl shifts when they came by my office, and that's another way of stabilizing it. You could go from a primary to a secondary carbocation, but tertiary is much more stable in this case. Yep. Yeah, you can have any sort of rearrangement, but you want to try to form your most stable carbocation available, right? All right, so the next step will be having this react with benzene. So this was a very steppy reaction. This will add in. Let me actually draw all of these. Let me rearrange this a bit. I know, I'm going to fill it all in here, guys. Let's see. Sorry, there we go. Oh man, this is getting crowded, so I'm going to do my best here. All right, so now we've got this aluminum tetrachloride complex. And this can act as a base to re-aromatize the ring. Giving us back our aromaticity. And we have this dimethyl group coming off now. Shoot. All right, what's the next step then? Do it all over again, right?
Professor, I have a question.
Mm-hmm.
So after you kick off the chlorine and all that other stuff, and then basically I know that when you do this, it kind of closes up and forms like a new ring system almost. But could you also add in another benzene ring there as well?
We'll talk about that. So I'm going to actually combine these steps into one step and have the chlorine pop off all at once here just to save some space. Otherwise, I'm going to run out of room.
I know I see why the other one is not unstable.
It's a really interesting question. You're on track.
Good job, Kareem.
Thanks, Adrian.
And I'll call this our Hydride Shift. We're going to move this hydrogen over. Sorry guys, I know this was a very steppy reaction, but I thought it was a very interesting one, which is why I chose it.
Where do you pick these from?
He did.
His brain.
Why?
He just has nightmares about this problem. It's on paper.
I mean, do they have like a teacher book of problems that you get a, probably?
I'll give you guys a hint. A lot of these problems I actually pull from the book. All right, so the question is, why doesn't a benzene come in and attack the carbocation?
Is it just sterics? I thought I assumed, but wouldn't you say
It's a combination of a couple things.
proximity?
The biggest thing is entropy. So if we think about the universe wants to be more disordered. Having two molecules come together is entropically disfavorable. We don't want to go from 2 moles to 1 mole. But if we cinch this in and actually do a cyclization, we're just going from 1 mole to 1 mole. That's not that entropically disfavored. So in this case, the major product you would get would be the cyclization of
The
this.
universe wants more chaos.
Yeah,
Exactly.
why?
Why does the universe want more chaos?
Yeah.
So think about if you spray perfume in a room. Why does the perfume not stay in one spot? Things want to be disordered. They want to move out. They want to be disorganized. It's the nature of our universe. So in this case, we're not increasing the, or we're not causing increased order. We're actually keeping it about the same. So the next step would be adding this in. So now we get this cyclic ring system.
You still have 2 mechanisms on the bottom.
I know, I'm trying to fill it all in. We've got bonds here. We've got a hydrogen here. And then the very last step will be our aluminum tetrachloride. It will come, grab this proton, clamp down, and restore aromaticity. Do we have to worry about stereoisomers?
Hope not, 'cause I didn't put it on there.
I'm with Adrian.
What do you guys think? Do we have to worry about stereoisomers?
No.
No, there's no stereocenters in this, so we don't have to worry about stereoisomers for this problem. The main product that we'll get out of this reaction will be this fused cyclic ring system that we've got here.
So you wouldn't at all observe the product of the benzene ring added?
Oftentimes when you do this, what you would observe is maybe a minor product that would be benzene added in, but the major product would be the cyclization. Most of the time, chemistry is not as clean as the book makes it out to be. You oftentimes get a mixture of products. Good question. All right, so let's switch back to chapter 19 on activators. And I actually want to go back and make a slight correction to what I was talking about yesterday. Yesterday we said that aromatic molecules with electron-donating substituents are activated, right? That means that electrons are being dumped into the ring, which makes the benzene a better nucleophile than it otherwise would be. And we said that examples of strong activators would be phenol, phenoxide, or amines, because they have lone pairs on the atom that's directly attached to the ring. And then we said we could rationalize this by drawing out all the resonance structures for phenol as an example. And when we do this, we get a hybrid structure where we've got partial negative charges on the ortho and para position. So in particular, groups that, or benzene rings that have electron donating groups with them are ortho para directors. The one thing I said that was a little bit off was I said that alkyl groups are moderate electron donors or activators. I'm going to change this. So let's cross this out and say weak.
That's cool.
Because I actually forgot about a class of compounds that's kind of in between alkyl groups and the strong electron donating groups. And these are obviously called moderate activators. So I'm going to slide these in here.
Well, which one's moderate?
So the weak one was the alkyl group, so I just crossed out weak or moderate and changed that to weak because alkyl groups are weakly electron donating due to hyperconjugation. Okay, so now let's fill in the gap. We've got moderate activators. And these are a little bit weird. So I'll draw out a few examples. So we've got one that's an ester. We've got one that's an amide where the amide's got a hydrogen on it. And we've also got other types of amides where the nitrogen can have an alkyl group coming off of it.
There is a lone pair on nitrogen, correct?
Yep, let me finish drawing these in.
Just making sure. I just want to make sure.
Yeah, to fill the octet rule, the nitrogen has a lone pair on it. All right, so up above I said anytime you've got an electron or an atom with a lone pair on that atom, that it can be electron donating. Now let's go down to the moderate activators. If we look over, we've got an oxygen with a lone pair directly attached to the ring, a nitrogen with a lone pair, and a nitrogen with a lone pair. Why wouldn't these be considered strongly electron donating?
Because
They resonate outside.
Lone pair's already been
They have other,
localized.
they have other atoms that.
No, I think you guys are definitely on the right track. So let's think about this.
Maybe they're competing.
it has more substituents.
I told Brian that.
We've got a competing resonance structure, right?
Yeah. Because isn't that group partly nitrogen?
It's not very big.
So in all of these examples, we have competing am I spelling competing right? Was it? All right, competing, oh my gosh, competing resonance occurring. It looks wrong.
It looked wrong.
I'm going to look it up later. This will bug me. All right, so we have competing resonance problems here, right? We have some resonance structures where the oxygen can donate in, and then we've got competing resonance structures where we can push those electrons out. So in these examples, these are all moderate activators. They don't exclusively donate into the ring. They can also pull electron density out of the ring. So these kind of fall in between alkyl groups and the strong electron donors. The weird exception to there's a lot of exceptions in this chapter. Does anybody remember the name of this parent group? Anisole. Anisole is a moderate
Even without the?
activator.
So what competing resonance is?
You're entirely correct. It doesn't have competing resonance, but because we have an alkyl group on there, the alkyl group is slightly electron donating, and so if we dump electrons into that ring, it doesn't stabilize it very well. So in this case, we're going to kind of accept this at face value that anisole is a moderate electron donator. It's not a strong electron donator as we might expect. It's one of those weird exceptions. Really, oftentimes chemists do these experiments, they see the results, and then they come up with a conclusion. Sometimes the explanations are a little iffy, but that's something that chemists are always working on improving. All right, so we've filled in that gap, and then we yesterday said that we have weak electron donators that don't involve resonance. They just simply involve hyperconjugation, which is not as strong as resonance. And then one thing I wanted to clarify too is we gave the example of making TNT, and we said because we have a methyl group, it's going to be an ortho-para activator. And then I should have said that we've got excess nitric acid and sulfuric acid, and if we do that, we can make TNT and install nitro groups in both the para and ortho positions. We can actually push this to get the trinitrated species.
So without the excess, it's just as well we wouldn't actually get TNT.
You would get one nitro group installed, and we're going to talk more about that later. Specifically, which position would be preferred? Would it be ortho or would it be para? Which one would be beneficial? Yep.
It's excess for both reagents or just one?
Yeah, excess for both reagents. Yep. Yep.
For the problem of the day that we got today, are we not assuming that sulfuric acid in excess?
So in the problem of the day, we had aluminum trichloride.
The one we got today.
The one we had today?
It didn't say.
Assume that it's not in excess. Assume it's one equivalent on the problem of the day. All right. So let's go to the flip side of the coin and go to deactivators. And I'm going to kind of quickly go through these, and we're going to just make a list of strong, moderate, and weak. So a strong deactivator is something with a very strongly electron withdrawing group. What's an example of a strongly electron withdrawing group? Close. Yeah. So a nitro group. Because if we have a nitro group, that nitrogen technically has a positive charge on it. So that's very electron withdrawing. So nitrobenzene is. Or if we've got some sort of alkylated amine where that nitrogen has a positive group, that's also very, very electron withdrawing. That nitrogen wants its electrons. The other one is if we have a trihalogenated group in a benzylic position. Why is this so electron withdrawing? I heard somebody say induction, right? If we've got 3 halogens, that's sucking a lot of electron density out of the ring just through induction, not by resonance. So all 3 of these are examples of strong deactivators. Now let's go to the moderate deactivators. All right. Yeah, you can try to memorize them, but try to use the tricks. Like I was saying, if there's a lone pair directly on a ring where it can only donate in, that's going to be a strong activator. If you've got a nitrogen with a positive charge, that's going to be a strong deactivator. So you can identify trends that make it a lot easier than just memorizing. All right, with moderate deactivators, they're electron withdrawing, but they aren't as electron withdrawing. And so an example might be a carbonyl group. Another example might be benzaldehydes. Another one might be the ester. But in this case, the oxygen on the ester isn't in between the carbonyl group and the ring. It's actually on the exterior side.
Why isn't that one a competing one?
So if you think about it, if the oxygen were to donate electrons in and out, that's not necessarily pulling electrons out of the ring, right? But if that oxygen were on the interior side, meaning between the benzene ring and the carbonyl group, then it would be competing. All right, so let's draw a couple more.
Are you going to know what's a moderate or not?
Yeah. I'm going to get a list going, and then we'll talk about why they're moderate. We've got amides. And then we've got sulfones, where we've got a sulfur attached. And then we've got nitrile groups. So all of these are examples of moderate deactivators. And let's actually go through and draw the resonance structure for the top left one, that ketone. And we'll take a look at why it's a moderate deactivator. And whenever I'm in doubt with these, I just try to draw the resonance structures and see what makes sense. So, can I do that? No, not without violating our octet rule. We get a Texas carbon, so it's simply not allowed. But what we can do, push electrons out and up. Now we've got a positive charge there. Let me try to clarify that a bit. And then our oxygen has a negative charge. And we can keep on doing this, right? Say, all right, let's move this around the ring. That gives us our positive charge in the para position. And we can keep on pushing this even further. Oh, let me slide this over a smidge more. And we get a positive charge in our other ortho position. And we can even show it going completely back to our original structure by doing that. So let's put these all in a bracket to indicate that they're resonance structures. And in particular, I'm really interested in showing the hybrid structure for this. So instead of showing all four of these, let's just put our equivalent sign and redraw this using the hybrid form. So if we think about where our charges are, the oxygen, oxygen has a partial negative. We've got a partial positive in both ortho positions and in the para position. So if we're looking at our ring, it's very electron withdrawn, right? We're sucking electron density out of the ring. So the interesting thing to think about is that nucleophilic attack is disfavored at what positions? So disfavored.
Para.
So think about what makes a good nucleophile. A good nucleophile is something with a partial negative, right? So in this case, nucleophilic attack is going to be disfavored at our positions with a partial positive, right? Because they're actually deficient in electrons, they don't have excess electrons. So in this case, nucleophilic attack is disfavored at the ortho and meta positions. So where do you think? Oh, sorry. Ortho and para positions, which means that the attack is going to occur where? Probably in the meta position. It's not going to occur at the positions where you have a partial positive, which means the only one left will be the meta position.
The ring is doing the attacking.
Yep. And that's simply because these other two are so disfavored, so we're going to attack either here or here to avoid those partial positive charges. Does that make sense? All right. And some people will be angry with me about this, but there's another weird exception.
I'm angry.
And I even wrote halogens, the weird exception. It's not my fault. It's the way the science is.
Yeah, but you teach it. It makes me guilty by association.
Don't kill the messenger.
No, you always kill the messenger.
All right. So if we look at X, where X is a halogen, it's got lone pairs on it, which means it can be an electron donator, right? But halogens are electron withdrawing, which means they're inductively going to take electrons out of the ring. So we've got competing things going here. So the question is, what wins out? And in this case, the ortho-para directing ability is due to the lone pairs. So in this case, it has lone pairs. That can donate into the ring. Which means that it's going to be an ortho-para director. So in this case, the inductive effect of halogens makes them weak deactivators, but they are still ortho-para directors. That means if we have an electrophilic aromatic substitution, it's going to occur in the ortho or para position, even though chlorine is a deactivator. They are ortho-para directors. So normally our deactivators are meta-directors. Halogens are the weird example where they still are ortho-para directors because of the lone pair directly on them. Does that make sense? It's the weird exception. It's the only one you have to memorize for the activators and deactivators that doesn't follow the rule very well. That and anisole, I guess. All right, so let's think about if we have more than one substituent. The examples I've given you either had electron withdrawing groups or electron donating groups, but what if we have competing electron donating and withdrawing groups? What would really happen there? So if we have multiple substituents, let's take an example here. I'm going to actually label these differently. Oh. I'm going to use different colors. So CH3, and I'll do NO2. What would the name of this molecule be? Yep, so the parent would be toluene. We've got a nitro in the 4 or para position, so this would be para-nitrotoluene. All right, now let's look at the nitro group. Is it an ortho-para director or a meta-director? It's electron withdrawing, which means it's going to be a meta-director, right? So where's meta to the nitro group? So if we look at it, this is meta to the nitro. And this one is meta. All right. So if we're looking at exclusively the nitro group, we could say it's going to install in one of those two positions. All right. What about the methyl group on the top? Where would that direct? Ortho and para, right? So we could say, in this case, it could go into this ortho position, or it could go in this ortho position. What about this one? There's already something there. So in this case, we can't have para attack simply because the nitro group is already occupying that position. All right. So we've done our analysis here. Let's say that we take this compound and we tried to do a halogenation or an electrophilic aromatic halogenation with bromine and iron tribromide. We can predict that it will occur exclusively at that upper carbon, not the lower carbon, right? So the key is it will always add to this one. It will not add here. Simply because both groups are favoring the insulation of the bromine in that particular position. So sometimes you have to step back and analyze every single substituent coming off of the ring, assess which positions they're directing to, and then kind of make a list at the end. So let's come up with a strategy that we can use for this. Need me to scroll up? No? I'm just moaning in general. All right. So the first thing to do is first identify your substituents and determine where they direct to, or where they direct. So for example, we said our methyl group was an ortho-para director, and then we labeled them. We said our nitro group was a meta director, and I drew an arrow to that position. So identify all your substituents and then label them. The next thing is if there are competing groups, or deactivators, the most powerful activator will dominate. And this is because electrophilic aromatic substitution always involves a nucleophilic attack from the ring. And so if you have a group strongly donating electrons, that's going to be the strongest influence on the reaction itself. All right, and then the very last one is if multiple sites are probable, go with the sterically accessible site. That means if we have two positions that are equal probability based on ortho-para directors, the attack will occur at the one that's least crowded, essentially. So sterics will win out in that case. And so let's take an example and kind of work through this using this rationale. All right, so I'm going to draw in all of these here, and I'm going to do it the same way where I'm going to label them in different colors. So I'll label this phenol as OH in blue. I'll label the methyl group CH3 in red, and then I'll label our nitro group NO2 in green. All right, let's start with the phenol, that OH. It has a lone pair. Is it going to be a ortho-para director or a meta director? What do you guys think? Ortho-para, because it's got the lone pair on the oxygen that can donate into the ring. It's going to favor electron density being in either the ortho or the para positions. So we can say, all right, it could add there. What about here? Nope, it's blocked by that methyl group, so we exclude that position. What about here? Nope, it's occupied, so we ignore that. So really the only position that would be available or favored to the phenol would be the position shown in blue. All right, what about the methyl group? Is that an ortho-para director or a meta director? Meta. Or wait? Ortho-para. Because methyl groups are weakly electron donating due to hyperconjugation. Electron donating groups will always be ortho-para directors. So in this case, we've got an ortho position there. We've got a para position there. and then the other ortho position is blocked by the phenol, right? All right, now let's go to the nitro group. Will the nitro group favor ortho-para or meta? Meta. All right, so it looks like we've got competing interests at play, right? We've got a methyl group that's favoring those other two carbons, and then the phenol and the nitro group are favoring where the blue-green arrows are positioned. So which one do you think is probably going to win?
The one with the two arrows. Yeah, right there.
So let's highlight it.
That has two things going at once.
Actually, let me change my colors here. So this position will win. Why is the phenol beating the methyl group as an activator? Because it's a way, way stronger activator. So in this case, phenol wins because it's the stronger activator.
I thought you said something about if they both were. Why is it because of that? I just would think because there's two spots that it could both go to, so that would win out.
Yeah, the more important thing to look at is Rule 2 here, where it says if there are competing activators or deactivators, the most powerful activator will dominate. So we're really looking for which one's donating the most electron density into the ring, because the overall driving force is a nucleophilic attack. So it's what's contributing the most electron density. Yeah. How do we know that phenol is stronger? So let's go back to our activator site. And we said that strong activators have lone pairs on the atom directly attached to the ring. And that's because they can donate electron density into the ring. And if this whole reaction is driven by nucleophilic attack, it's going to occur on one of these positions that has a negative charge. So the ortho-para positions are favored. An alkyl group is electron donating insofar as it donates weakly from hyperconjugation.
And the NO2 would be a
Exactly. A nitro group would be a deactivator because you have a nitrogen with a positive charge pulling electron density out of the ring. All right. So let's switch to steric effects really quick. And this is a pretty simple concept. When you have ortho-para directors, there is a judgment call. But it's an easy judgment call.
My judgment in chemistry, organic chemistry, is not
So let's take some examples.
up to par.
Example 1, we'll take toluene. Example 2, example 2 will be tert-butylbenzene. All right, we know methyl groups or alkyl groups in general are going to be ortho-para directors. In this case, it will actually attack the ortho position because both sites are very available, right? The methyl group's not very big, at least compared to a tert-butyl group. And you've got twice as many ortho positions as you do para positions, right? So statistically, you can run into either side twice as likely as the para position itself. So in this case, you will get a mixture. But this one will be your major, and this one will be your minor. However, with the tert-butyl group, do you think that ortho attack is going to occur very readily? Yeah, it's too big and bulky to have a bromine come and sneak in there. So in this case, you might observe a very, very, very tiny bit of the orthobrominated, but it's going to be minuscule. And that simply is because the site is too crowded. So if we do have an activator where you have to decide is it going to be ortho or para, look at how big it is. Usually the only ones where we observe a predominant portion of ortho is with a methyl group. Any other group that's bigger than a methyl group will tend to favor para substitution just simply because it's more sterically accessible. So the general trend is most of the time the para position is favored. Oh.
What was that?
There we go. Is
That Florida trip.
scoot it up.
Over. There you go. Too crowded.
I hope you reuse these lectures next year so you hear this.
Unless the activator is very small, like the size of a methyl group, then your ortho position will be favored. All right, I think we have time to do our last section for today.
How are we doing another practice problem?
We're gonna do practice problems. All right, let's actually jump straight into a practice problem.
Yeah. From the previous stuff.
She's like, yeah, no.
I have 2 arrows.
Because this is a multiple step synthesis.
Oh, is that what that means? I keep seeing it in the book.
Okay.
I'm serious. I didn't know what they were doing.
All right, so in this example,
You just said it wouldn't do that.
yeah, I did. But in this example, we have to use some trickery. So if we look at our last example, we said that bromine, if we just did electrophilic aromatic substitution, would install into para position, but we need to get the orthobromination,
Peroxide.
not peroxide.
When in doubt, that's some peroxide.
So one really useful tool we have is use reversible sulfonation.
Oh, of course.
Wait a minute, I think it's called what was in the book like that.
How wasn't I thinking about that?
I just did that.
All right, so let's take the example.
Yeah, can you do that? Can you just work it the right way and then put those arrows, the backward arrows?
You can. I just wanted to show the overall scheme. So let's do sulfonation. What reagents would we need to do a sulfonation? So get this SO3H on there. Fuming sulfurics. All right, so now we've got sulfuric acid, or a sulfonate group on there. Is the sulfonate group electron withdrawing or donating? It's withdrawing, right? So will it be ortho, para, or meta director? So if we look at this group, it's going to favor the meta position because it's electron withdrawing. What about the alkyl group? Will that favor orthopara or meta? Orthopara. So again, we'll favor this position. So we're favoring that top carbon now, which is great because that's where we want our bromine to go. So if we add in bromine and our iron tribromide, we're going to probably have to heat this up quite a bit to beat out the steric problems here. But we can still drive it there because that para position is now blocked by that sulfonate group. All right, now how do we get that sulfonate group off to give us our final product? Dilute sulfuric acid. All right. So we've solved that problem of outcompeting sterics and actually installing it in the correct position we want by using reversible sulfonation. And this is a really, really powerful technique that we're going to use in synthesis a fair amount. Oh. You guys got it?
It's like when we work backwards in synthesis, right?
Yep, it's like when we work backwards. But for some of these, tomorrow what we're going to do is develop better synthetic strategies for these types of reactions. Because oftentimes when you've got 4 substituents on there, it becomes overwhelming to work backwards.
Why don't we just do the double arrow thing?
You can do it either way. Either way is perfectly acceptable. All right, I think we're going to stop there for today.
In the book, they did like...
Here, let me stop the recording.